Hello. What I'm going to explain and demonstrate for you today is a new piece of software developed from Rocket Software that we're pretty excited about called Virtual Parallel Data. What Virtual Parallel Data does is it allows multiple independent SQL requests to share a single result set. The result set that is shared is actually a 64-bit memory object, which will be shared by all the SQL requests to generate multiple SQL result sets. So the data is read physically one time into a memory object buffer, and then each of the simultaneous SQL requests would share that memory buffer to get to the data. The front ends that support it right now are the loader, Java or JDBC driver, the studio, and batch DS spoofy. The backend data sources that are currently supported are sequential and tape, VSAM and IAM, Adabase, ZFS, log streams, MQ, and we're also actively developing other backend data sources as this video is being created. When you talk about virtual parallel data, you have some parameters that are defined, and this table shows the specific parameter names that are defined for DS Spoofy, the loader, and JDBC. The first of which is what you would call a group name. And then you define how many members are going to be in the group. And then you also define the group formation timeout. If you don't set that, the default is 60 seconds. And then you also define the number of I/O threads, which are the physical I/O threads that are going to be used to physically read the data into the memory object. So what happens with virtual parallel data is that VPD requests are joined in a named group. Each request specifies the name of the group. The first request to arrive creates the group, and I/O begins immediately. Requests arriving within the defined time interval are placed into the same group. And then the group is closed when the last request arrives or the timeout is reached. Once the group is closed, the buffer can be wrapped and reused. The backend I/O is done once and buffered in one or more large 64-bit memory objects, and then each of the SQL requests would access that 64-bit memory object, and all group members would share the same buffered results. And the last bullet is important to note that each VPD request can specify its own degree of parallelism using MRC, or map reduced client. We call that asymmetrical parallelism, and I'll demonstrate that in the demos. With that said, let's move forward to the demo at this time. In this first demonstration, I'm going to demonstrate using DS Spoofy to read a sequential file and drive 5 different reports from that sequential file. So there'll be 5 different jobs that are submit. Each have had the group name defined. They've defined how many members are in the group, which are 5 because 5 jobs will be submit. It's defined how many physical I/O threads to use to load the data, in this case 6. And for this first particular report, where it's selecting from the day of the week Thursday, I know the row count is rather small, so I've set an MRC value of 2, which means it will use 2 SQL threads. It's also worth noting that I have a parameter called interim set to 1. That means that it's for every 1 second, it's going to report how many rows have been read by the MRC threads. The second job, which is reading Friday, which has slightly more rows, has all the same parm values except for it's going to use 1 extra SQL engine thread, and it has a count of 3. The third job, which is reading Wednesday, has even more rows, and it has all the same parm values, but an MRC value of 4. The next job, which is reading Monday, even has more rows and has a larger MRC value of 5. And the final job, which is going to read Tuesday is going to return the most rows and has an MRC value of 6 and will use 6 SQL threads. And when you submit this job, you'll see that all 5 jobs are running at the same time. There's the jobs running. There the jobs have finished. And when we look at each of these jobs, we can look at the first one, which we knew was using an MRC value of 2. And we can see that in the first second it had read 28,000 rows, and each of the SQL threads had split that IO between them. And then 1 second later, or 2 seconds in, it had read 33,000. 3 seconds in, it had read 39,000. And in total, it read 40,000. Those were split between the SQL engine or MRC thread counts, and it read those in 8.3 seconds and generated this report. If you look at the second job, which would have had slightly more rows read, you can see the MRC value was 3. And in total, it read 100,000 rows and split those between the MRC thread count and did it in 8.3 seconds. The next job, which would read even slightly more rows, read 446,000, all split amongst the SQL or MRC threads, and did it again in 8.3 seconds. The next job read 1.8 million rows, had an MRC count of 5, split it against the IOs against the 5 threads, and did it in 8.3 seconds again. And finally, the largest, it read 2.5 million rows, had an MRC value of 6, so it split the 2.5 million IOs along the 6 MRC or SQL threads, and did that also within 8.3 seconds and generated the report. Let's move now to this next demo, which will be a demo using the loader. In this job, I'm going to demonstrate accessing SMF data and loading 3 different tables to the accelerator. This is a good use case for the loader for SMF data because you have to pass all the SMF data regardless of what type you're reading. So using VPD, it allows you to physically read the data only one time into the memory object buffers, and then each of these load jobs will access that same buffer to load the table to the accelerator. This use case really shows the polymorphic benefits of VPD, as it will be reading the 3 different SMF record types all from within the same file. So in this first job, it is going to access SMF 20, and it's going to create a table in the accelerator called SMF 20. If we look at the actual load step, we can see it's going to select asterisk from SMF 20 map and load it into the accelerator. The VPD group has been defined for each of these 3 jobs that are going to run. It has a value of HLV 665G. The VPD member count has been defined to 3 because there's going to be 3 different jobs that are submit. The VPD IO thread count that's going to be used to physically read the data has been set to 6. And in this particular case where I'm reading SMF 20, I know it's rather small in the number of rows that will be returned. So the MRC count has been set to 2. So it will use 2 SQL threads. In the next job, it's going to read and create an SMF 15 table. And if I look at the load step, I can see in the load step that it has the same group name, same members, same 6 IO threads. In this case, SMF15 was going to return more rows, so I've bumped the MRC count to 4. And in the final job, it's going to access the SMF type 30 table, which even has more rows. And if you look at the load job, you'll see, of course, the same group, same number of members, same physical IOs as 6, but the load task or MRC value is going to be set to 6, so it's going to use 6 SQL threads. And when I submit this job, we'll see it run. There they finished. And if we look at each of these jobs, the first one, which was accessing the SMF 20 table and created that table in the accelerator, it accessed 8,990 rows, which was about 3 megabytes of data in 2 seconds. If we look at the second one, it accessed 102,000 rows, which was 123 megabyte of data in 4 seconds. And finally, the last one was 173,000 rows loaded, which was 72 megabyte in 2 seconds. So this demonstrates using asymmetrical parallelism how you can fine-tune each of your load jobs depending upon the volume of rows being returned using a different MRC value so that different amounts of SQL engine threads would be used to load the data. This example showed you the benefits of asymmetrical parallelism and tuning each job with different MRC values so that as the number of rows increased between the jobs, the load time for each job did not. It's also worth mentioning, if you haven't derived it already, that one of the big benefits of VPD is data consistency, in that you're reading the data one time into a memory object, and all SQL requests then access that same physical data from that memory object. So you're going to have consistency in your result sets. Versus not using VPD where uh, the data itself could change on the fly between the running of one job and the running of a second job, where with VPD you're not going to get that. It's also worth mentioning that here today I just demonstrated a DS spoofy example and a loader example, but you could also have a VPD group that had a loader job like one of these that we just ran, but it also one of the other jobs in the VPD group could be uh, a, a a access to like Hadoop through TCP/IP. There's really no limit to what you can do or no restrictions on what uh, these jobs have to be that make up the group. Well, that concludes the demo for today of VPD or virtual parallel data, uh, also using MRC or what we like to call the asymmetrical parallelism. I hope you enjoyed it and look forward to seeing you in the next video.